Right, so this is lecture 5. Today we are going to learn about different groundwater remediation techniques. Last class we learned about how groundwater can be polluted and how to calculate how far the pollutants can migrate. So today we are going to learn more about how you can actually treat it. So first, I want to suggest that these are the announcement. Um, I didn't release the homework last week because we didn't really cover the enough topics for the homeworks to for you to answer the questions that's on homework too. So that's why I released today. Everything that we cover today is going to complete everything that you need to know to answer homework 2 questions. And project topic we'll discuss because I got some emails and I'll give you some guidelines earlier in the class about what I really expect when I say project topic. It should not take more than 10 minutes to for the groups to actually come up with a topic because it's not necessarily once you decide the topic and send it to me, that's fixed. It's meant for a conversation. So really, you should not worry about whether your topic is right or wrong and all that stuff. Um, so you should write your thoughts. That's how we should approach this particular assignment. Again, project assignment, project topic is due next class, not next week, next class, which is 21st on Thursday. Again, what I expect you to write is the titles and scope. I'll just get back to that one. And the homework 2 is due again on January 26th. Um, and I'll show you the homework. So these are the questions because some of the questions are relevant for what we are going to learn today. So that's why I want you to just know so that when you see the topics, you know how to answer them. So this particular question is more about how much of the oxidant, which is KMnO4, these are oxidant. So the question was how much of these oxidants is needed to treat certain volume of groundwater. So the pollute that so that means you need to know use the equations to answer that questions. This equation tell how much moles of potassium permanganate, which is the oxidants needed to treat 1 moles of this particular pollutant. So as long as you know how much moles of pollutants in your groundwater, you should be able to answer that. Next questions are related to how far a pollutant can migrate or how much was the capture zone width for a groundwater well and all that. So anyway, so these are the things you already know from CE153 class. I'm just covering again to some extent. Again, most of the questions related to this class are related. Um, some of the questions you already know from CE153. If you don't remember those, I encourage you to go back to those presentations file. But I'll cover at least some basic. That way you don't, even if you didn't take that class, you should not worry about it. This is the results of quiz 1. 55. Albert, you have a questions? I saw somebody raise a hand. Uh, go ahead, ask questions when I'm talking anything. You don't have to wait for me because sometimes I probably didn't see the hand raised. So don't be worried about interrupting me. If you have a really emergent question, you can ask. Okay, so or just put the question on the comment. That way I get to it every 10-15 minutes. All right, so this is the quiz results. 9.11 is the average, which is more than 91%, which is a good score. And this is the distributions of the class. As you see, majority of the students get more than 9. This is up to 9.5 to 10. That means these are above 9. And there are some scores below 9, but that's not a really no. You should not worry too much because these are best of 4 quiz. You still have another best 3 of 4. So you have another 3 quiz to take to do well. And also, I want to point out the total 55 students took the quiz. So that means two students didn't attempt it. Again, it's not going to affect your score unless you also not attempt another quiz, because now you just have to take the next three quizzes and that's your score. All right, so that's overall, this was this was a easy quiz, as I expect that you should answer the questions. And the other quiz will be very similar to this kind. So everything you learn in the class will be part of the quiz. All right. So any questions before we get to the learning objective of today's class? I didn't see any questions, so that means we can continue. All right. So learning objectives. So today you are going to, as I said, learn about how to actually treat groundwater. You learned in last class that groundwater contamination can happen because of accidents or spilling, all that. So we got to make sure that to treat them. And so there are many different ways to treat it. And so you are going to learn about the ex-situ method. Ex-situ method means you remove the groundwater from aquifer and um, then you treat it outside, and then you dump the same water or re-inject the same groundwater, treated groundwater back to aquifer. So ex-situ means outside the aquifer. Um, and then you'll learn about estimating the capture zone, because the first step of ex-situ treatments, you capture the contaminated groundwater. So how do you know where to put those capture well? So that's a part of the capture zone calculations. You should be able to design that based on the equations that will provide. Again, you learned that in CE163. I'll just provide the more overview on that. Then you, at the end, you learn about three or four different types of ex-situ treatments, which are commonly used, at least the basic overview of it. And we'll learn about one specific method, advanced oxidation method, today in this class. And the second half of the class, we'll actually discuss your own projects. So I know that many of you want to meet. So we can discuss during the class so that you know other students can also benefit how to write your scope. So this is again open-ended discussion, so we should not worry about um, sharing your thoughts. All right, so based on what we learned last time, how far groundwater pollutants can migrate, let's see how many of you can answer these questions. So I'm going to release these quiz questions. You have choice A, B, C. So I said that if oil spill occur in two aquifers used for drinking water, which one of them poses a greater risk for spreading the pollutants? So you have sandy aquifers, silt aquifers, clay aquifer. This just says what kind of. So it says which has the most risk spreading the pollutants. Spreading means how far it can migrate, not how can it can disperse. So you have 30 more seconds to answer these questions. Again, it should be related to hydraulic conductivity. All right, so let's say end poll. Um, so as you see, most of you say the answer is A. Um, the reason is the question was how far the pollutants, which has a greater risk. Risk is high when the pollutants move faster, and pollutant move faster if water move faster, or if the uh, aquifer has less adsorption capacity. I didn't tell anything about adsorption, so that means you have to guess based on the how far water can move. Again, based on the particle size, you know that sandy soil, sandy aquifers are high hydraulic conductivity. So that means they can allow water to move much faster. So that means pollutant can move much faster. Right. So that's what you should know before from the last class. All right. So let's see discussion of project topics. I just want to give you some examples because I know that some of you send me the topics. So the topic means you got to have a title. Okay, without a title, that means that's not a topic. So you got to have a working title. Again, it does. It's not. It's going to change over time. You can continue to edit your title. So, but at least you should start with that. And you must have listed the team members. So it's not so that I know who are in the team. So the team should not exceed more than 8 students. It can have lower students. If your team begin with 6 persons and now some students probably drop out, let me know. I can add another students there, or I can suggest students to join your team. Um, it must have also a short description of the scope. The reason I ask this question is if you say, let's say your one of the team says that we are going to work on plastics, so that have a title. But if you say that I want to work on a microplastic problem, it's not specific enough. All I know is a microplastic, but I don't know what aspect of microplastic you want to learn. Is this all about minimizing the plastics use or recycling more plastics? Or is this about using the plastic waste as a different product? They are all different kind of projects. So you got to make it narrow. If you make it very broad, it's very difficult to decide what actually to include. So you'll have difficulty finishing the project. So that's why I always encourage you to make it narrower. Uh, Again, this is a working example, so that doesn't mean that you whatever you decide, it's not going to you're not going to lose the points for that. I'll give you that kind of comment. So this is again a discussion. This is not an end goal. Okay. So don't worry about losing point for sharing. You can discuss with me anytime and set a time with me, but it's not needed for this particular assignment. So again, what not to do is don't make the project very broad. Okay, it should be a little bit specific. And do not pick a projects where you are not confident about finding informations online because you are going to search for it. So you can do a search, Google search, and see what information out there. That will at least give you indications. Again, the second point is not that of a mistake because when you'll find out, you'll also change the topic to some extent or the scope. You'll redefine the scope. So again, just because you submit something doesn't mean that you are going to, we are going to work on exactly that's bounded. Okay. Um, all right. So that's all. And the second thing I want to suggest is that you should create a Google Doc. It's something. Um, how do you submission? You should create a project documents Google Doc, write those titles, write the scope, and this is where you will continue to update. And just share the link with me. That way I can give you comments, and what it does, it all the your group members can work on the same document simultaneously. So that makes it a lot easier, and you don't have to wait for me to I can give you comments before even, let's say you submitted today, I can give you comments. You can edit it and send it back again. Means just let me know. That way it's I'm working with you, so just don't forget that I'm also part of your team. And I'll give you feedback every steps. So that's why the accuracy is not a factor here. This is all about project, working as a project. So create a Google Doc and submit, send the link. Okay. And meeting with me, as I said, not needed. We'll have a meeting after this class today, or at least the second half. But when you have at least written the outline, that's where you are required to meet with me or the TA. The reason is we want to be more closely involved in that stage so that your workload is not too much and you are not lost. Any questions? All right, so let's get quickly learn about remediation method. So think of last class you learned that there is a location which is polluted. And let's imagine that the groundwater aquifer in Los Angeles is polluted. So how you are going to approach it? The very first thing is you have to decide is what's the objective here. Is this objective to remove all pollutants or just remove to a certain extent? So you have to create your boundary. What's the end goal? So that's what we call remediation objective. That means you decide what purpose to what extent, because treating something, removing let's say 60% of a pollutant is not expensive. Removing to 90%, it requires a lot different technology. Removing to 99.99% require even much different type of technology. So that's why it's very important to first decide what's your goal, what's the threshold that you want to remove. And second is to decide also to what types of pollutants you are going to remove. And so these are the like your broad goal. Obviously, you want to treat it to the extent you have to define. That's the first step. And the second step is to decide different interim remediation or remedial measures, because you have to break the entire project into small step. Okay. For instance, if you say that I'm going to treat the entire groundwater, there are a lot of different complexities. So you could have a small thing, small milestone. So these are, again, you don't need to know the details, but this is something to be aware of when you're designing your own projects. You'll think of all these different steps based on what's your project, and we'll learn through that. Just know the step. Again, these all the class are tailored towards your project. So the actual concept and theories are very simple. You already learned many of them in the CEE153. So this is designed for, again, just to apply those concepts. Then the second thing is feasibility study. This is where you are going to look for the reports. If that site is not well characterized, you are going to do that characterizations. So for your case, that's not the case, because you are not going to actually do contamination assessment by analyzing groundwater. You are going to look for report. So that means you are going to look for all these other aspects. Um, First thing is to look for is, can we actually treat this pollutant? For instance, let's say you found out this groundwater is polluted with PFAS. That means you have to now think of what are the different technologies that are out there which can actually remove PFAS. You cannot just use something just because that's part of the class. Then you have to go beyond the class and look for treatment technologies. And that's where it will help you. But first you have to think of that. Second thing you have to define is how long. If this project means the treatment goal, is this 5-year projects, 10-year projects, or 20 years, or what's the time scale you have? Okay. So those are things you have to define. It's not like you have flexibility, but roughly typical projects last uh, around 10 years maximum. Okay, you don't want to have a design, because the operational cost is much more expensive than material cost. So typical remediation projects should not exceed more than 10 years. On average, 5 year is a good time. Okay, unless it's a bioremediations where you're not actually doing much inactively, so that means it can extend for longer year, but you are not doing it anything. You are just monitoring it. Then you have to think of a cost, because you can always say that I'm going to use this technology, but if it is too expensive, you're not going to use it. So you have to think of all these feasibility studies before you choose. So these are different types of remedial actions. Um, for instance, it doesn't have to be like actual treatment technology. It could be just remediation. There could be a control. For instance, if there is a spill coming from a particular site, all you have to do is close that site. You say that nobody can use these products anymore in that site. So that could be part of the remediation goal. So do not just constrain just technology. It could be also minimizing the waste. And there is also another aspect. Anytime you find a site and you want to do something about, think of if I don't do anything, if I don't do add any more pollutants, how long the pollutants will last there? Because nature can actually take care of many pollutants by itself. So first thing is that natural attenuations is important to consider. Because if natural attenuation is sufficient, you don't have to do anything. So your project could be just saying that, okay, this is my recommendation in natural attenuations, and we'll just do all the calculations, saying that in this site we don't have to do much as long as we are not adding more pollutant. It can also remove pollutants by itself. And then the third one is most like a technological interventions where you have some kind of treatment design to minimize the spreading of pollutant. It could be adding a groundwater pumping well so that you can capture the pollutants and treat it, or it could be adding a barrier so that the pollutant do not leave that site. Um, so these are the other aspect you can do it. But as you see, the natural attenuation is the very first step that everybody should consider for their site. So how do you know whether there is a natural attenuations? The way we find that out in nature is we put this monitoring well. So imagine you have a source here, and this source is um, the pollutants are moving from here. Okay, let's say this is. And how do you know whether these pollutants can degrade by itself? The way to do it is you put a monitor. Let's say this is the source and this is groundwater. This is subsurface. So you put monitoring well here, okay? And you collect samples and you do that. You take samples. First thing is you limit the source. That means you remove the source of the pollutions. So that way there is no continuous um, release of pollutants. Once you limit the source, now you have to see monitor how long before the pollutants can dissipate by itself. So then you collect groundwaters and you take observations at different time. And so what you are going to do is you plot the graph. This is where the monitoring data look like. Time in months or years. And then you collect samples at different time at the same groundwater well. And the pollutant concentration decrease. Let's say this is how the pollutant concentration decrease. And then you have to first think of what's your, this is pollutant. And first thing you have to see is what's your remediation goal? For instance, let's say this is your goal was to have the pollutant concentration. This is your, let's say, goal. As long as your pollutant concentration is that or lower, then you don't have to do anything. So that means what you see here is if you wait, let's say this is roughly, this is let's say 2 years. Based on the modeling or other things, if you see, usually you see this number and then you predict how far it can go. So what you predict here is that in 2 years, your concentration at that groundwater well will be below your limit, the threshold that you wanted to treat to. So that means in this site, you don't have to do anything. If it is within 2 years, you can get the pollutant below the threshold or below the risk level. You don't have to do any remediation actions. All you have to do is minimize the source. You are done with that. Okay, so that's how it works. So now for this natural attenuation to occur, what kind of um, engineering method you need to learn? The only way you can learn from here is the how to make the wells, how to design those wells, where to place the well. So first, obviously, you are not going to learn how to make groundwater well. It's basically digging a big the PVC pipe into the ground, that's all the groundwater well. Typically, they are like within 2 inch or 1 or 2 inch diameters. So those are the basically you are passing through the ground, and it can goes as deep as possible. Um, and the challenge here is how where to look for that well. So how do you know where the location should be? So obviously that's based on the initial monitoring data. You take different random locations and measure the concentrations. Based on that, you create a map, and then then based on that map, you strategically put the locations, and then you pump all the water if you want to capture it. So that's why what we are going to learn in this next couple of slides is how to calculate that capture zone. But before that, there are some remediation action, like as you said, you have to remove the source. How do you remove the source? The first thing to removing source, usually source in the surface. You can excavate or dig all the entire contaminated soil from the surface and dispose it. So that's the first method. This method usually is okay if you have a very small located, a very concentrated area. For instance, if you have a gas station, you can do that one. You can dig the entire soil and replace it with a clean soil. But if you the pollutant site, which is several hundreds and hundreds of feet or thousands of feet long, or the area is much higher, then this digging soil is not going to be cheaper. It will be much more expensive. In this case, you cannot remove the source. You have to treat it right there. And then you have to think of bioremediations or oxidations or any other types of soil treatment technology. That's something we'll learn later. But just know that removing source is the key here. And most of the source removal is basically excavations, as long as the area is small. So this is choose this if the cost of excavation is low. Okay. If the cost is very high, you have to start thinking of other treatment technology. If cost of is high, then soil. There are many soil treatment methods. It could be just burning the soil by applying heat. It could be fixation. So we'll learn all that later, but just know that this is how you can decide. Okay. And bioremediation is most popular because there you don't have to do much. You use the natural methods to remove some pollutants. But bioremediation sometimes is very slow and doesn't work a lot of places because not all pollutants can be removed by bacteria or fungi efficiently. So you have to think of all that. All right. So now that you learn you remove the source one of those way, you have two choices. Either you use ex-situ method where you pump groundwater like you see here. Your contaminated groundwater is uh, is pumped. Then you treat using any other treatment method. So this is a treatment method, and then you reinject back the treated groundwater um, in the upstreams. That way you replace that groundwater or contaminated groundwater with clean groundwater. So this is called pump and treat method. Pump and treat method means you pump the groundwater and then treat. And this particular method was very popular in 1990s because that's the earliest time they thought that all you have to do is just pump all the groundwater and treat it and put it back. You exactly know what you can do. Um, but later they realized this is not that simple. First, pump and treat method relies on one assumption that you can actually pump all the pollutants or polluted groundwater, which is easy if you have a sandy aquifer. If it is not sandy aquifer, the soil itself will trap a lot of pollutants, and then it's become almost impossible to remove everything because they will be trapped and they will release slowly. That means these pop and treat methods is not going to be efficient in clay soil, and it will take like hundreds of years. And pumping is always energy intensive process. So that means if you pump it for 10 years, imagine you are running a pump for 10 years. The cost of energy is so humongous, and then you have to treat them. So pump and treat method is no longer very effective. Anytime you have use pump and treat method, that's only for limited time, so that you remove the bulk amount of pollutant first, then you have to use something else. So pump and treat method is not used single-handedly for any sites anymore because of that reason. And then you have in situ method, which become more popular now, which is essentially you somehow activate that process that makes the pollutant degrade or remove from that site. So we'll go through that all different steps. Just to I create this different name here so that you know what they look like or what they are called. Soil vapor extraction, as the name sounds like, you just have to vaporize or the um, collect the vapors from the soil. So that means this method is only applicable for volatile organic pollutants because it has to be in the vapor. Air sparging, the same thing. You sparge air through it so that all the volatile pollutants will remove the flush out of the system. Then you have soil flushing. Then the vitrification, which is like I said, you can apply heat. That heat can actually vaporize or the volatilize some of the pollutants. Solidifications is more about making the pollutants precipitate and stock inside it. Think of cement. If you create a cement is not going to break or dissolve very easily. If you have a cement concrete outside, that's why the building lasts for longer. So all you are doing is making cement right in the soil so that you can um, make the pollutants stay there for a long period of time. So that's solidifications. Then you have oxidation reduction, where you apply some kind of reactants that will destroy that pollutant, which is homework number one. By far, the most popular method is bioremediations now because it is using natural method. It doesn't have much side effect. Um, it can very less likely to cause harmful byproducts, but there are also bacteria can also produce harmful byproduct, but few cases only. And then the another one is permeable reactive barrier, which is you put a barrier here so that the pollutants as move through the barrier, it capture it and degrade it. So these are the different principle of it. So I'll share a slides or not slides, the handout so that you know each process a little bit. We are not going to cover all of them. The reason is it's not that you have to apply all of these techniques into your site. But if you apply for any of them and it's not covered in the class, I will help you find those informations. Okay. We'll just go through a most common method. So as you see these slides, Ex-situ remediation, again, the principle like you see, you have a capture zone, you which is basically downstream. And you capture the pollutants in this well. You then you treat them inside the whatever the reactor you have. In this particular case, it is a bioreactors. So what you do is you add nutrients, you add substrates or food for the bacteria, and you inject the microorganism that actually remove those pollutants. You basically create a bioreactor in the systems. And as it remove the pollutants, then you have a clean water that you are injecting back into downstream, not downstream, upstream, so that you are replacing the contaminated water with a treated water. So this is ex-situ method. And again, this is, I just want to re-emphasize, it's most used method before, but it's become most ineffective because of the soil constraint. Soil constraint means it doesn't work if soil has clay or impermeable zone. That means any pollutants that is trapped inside those impermeable zone, is going to be harder to extract. So that means it works well when the hydraulic conductivity aquifer is high. That means if the sand is soil. So these are the quiz questions. Basically, I'll ask you what kind of pump and treat method where it doesn't work. So I'll give you options, then you'll know based on this concept. So that means this system will not work if there is a location which you cannot extract water from. And so again, let's assume that we can extract. That means you have to first put this kind of extraction well. As you see, this extraction well, if you see from the top, this is what it looked like. You put extraction well here. These are the groundwater coming from here. Based on how fast you are pumping, you create this is called a cone of depression. That means this is the capture zone. So that means any groundwater that comes from within this capture zone will be treated. Anything that is above the streamline, this will not be treated. So why it is important? For instance, here is the assessment slide. So this is the plume slide. Let's say your groundwater, you want to capture this plume here. So that means if the groundwater, I don't know exactly which directions, let's assume groundwater is moving these directions. So that means you have to make a groundwater well, at least here or other side, and then pump. And based on how fast you can pump, it will create a capture zone. If the pumping rate is higher, it will create bigger and bigger capture zone. But there is a limit to how fast you can pump because it's also energy intensive. So sometimes it's much cheaper to have multiple well than having one big well, okay, because of the limitation of soil heterogeneity. So what normally people do is they sometimes also make multiple well. So this is one zone, this is second zone, this is third zone. That way you can capture all the polluted water. So that means you have to know how to calculate those capture zone based on equation. So again, I'm not going to derive these equations. I just want to show that this derivation of what is the flow rate that you have to capture or different radius of the capture zone depends on the flow rate and hydraulic conductivity. And so we use Darcy's law to derive this equation in CEE163. You don't need to know the derivations, but just know the concept. So here it is written unconfined aquifer, the flow rate is directly proportional to the K hydraulic conductivity and area of the well, whatever the well that you are capturing water from, and then the head differences, how far the head drops as you pump water. So this is what the head difference means. If you start pumping water, the groundwater well will drop down. So that means the head will vary as you go farther and farther. Mostly the head is the lowest at the well, then it increases as you go further. So this is called um, zone of influence. That means if you pump at certain rate, within this area, all the water will be experiencing that drag. Beyond that zone, you will not experience any head differences. So that means this is the zone of influence or the cone of depression. So that means beyond this one, your dH equal to 0 if so I'm just writing that if R is greater than R influence, that means that's the maximum um, R within which you will experience a head drop. Okay, so this is your or R max within which your head drops. Okay, so there's a relationship between these radius and the head. Okay, and if you use this equation, you will be able to calculate that. So this is just for unconfined aquifer. You also have the same equation for a confined aquifer, which is written here. So again, it's the same concept. The difference here is that your aquifer is only the same thickness. Here, your head drops are different from how it looks here. Your aquifer thickness was not there before, but now you have aquifer thickness, which is B. Again, you put the same equations, and if you derive this or integrate it, you will get this answer. Okay. So for this class, all you have to know is these two equations. And what does that mean? All it means is that if you pump at certain flow rate, you can determine how the head is going to drop at different radius from the pumping well. Okay. So now let's do the example. This example is similar to homework question. So let's solve it. And that way you'll know how to do that in the homework. All right. So determining K from a cone of depression. Suppose a well of 0.3 meters in diameter has been pumped at a rate of 6,000 cubic meter per day for a long time, so that the steady state condition applies. Steady state means the heads at any location is not changing with time. Okay. And all these equation over here that assume steady states. That means it's not changing. The head is not dropping or changing at that well with time. An observation well located 30 meters from the pumping well, so that's written here, 30 meters, um, has been drawn down by 1 meter. So one of the term here is drawdown. Drawdown. What is drawdown? So as you see, there are a couple of things I keep mentioning. One is the head. Head means the height of groundwater in that well. Okay, so that's head. Drawdown means now before you start pumping, there was a groundwater elevation, which is here written. Okay, that's dash line is the original water table. So once you start pumping, it's going to decrease, and whatever that amount decrease is called drawdown. Okay, so that's means original ground water level minus head or water level. Okay, so that means in this case, the drawdown here is this. Okay, and this is the head or levels after the pumping starts. Okay, so the drawdown is the difference. So that means if you know the original water tables and you know the drawdown, you can calculate the head. That's all it means. So here it says the drawdown at 30 meters. So I'm going to write R. If R equal to 30 meters, let's say R equal to 30 meters. Your drawdown, which I'm going to write, let's say G is the drawdown, is 1 meter. That means head, which is what I'm writing, should be the original water table height, which is somewhere written. Let's see, the original water table height is what? 30 meters. Okay, so that's the original. This is the 30 meters, original water table height. 30 meters minus 1 meter. So that will be 29 meter. So that's written here. Okay. And then it says another observation well at 100 meter distance. So that means R2 equal to 100 meter. G2 would be 0.5 meters. That means S2 is 30 meter minus 0.5. So that's 29.5 meters. So it makes sense. As you move further from the extraction well, the head is going to increase. The well extends completely through an unconfined aquifer with 30 meter mark. So this is the maximum width here. Okay. So it's ask you what is and then it also give you Q. The flow rate and the pumping well is 6,000 meter cube per day. And the extraction well, the diameters is 0.3. So the extraction well, the diameter of the extraction well is, let's say, right, D0 is 0.3 meter. That means if you take the radius of that extraction well, so that's, let's say, call R0 extraction well, this will be 0.3 divided by 2. So this will be 0.15 meter. Okay. So now you have three different R. You have one Q value. All I ask is what's the K? Okay, hydraulic conductivity. So K, if you go back to the unconfined aquifer, which is here, you know these equations. All I ask is the K value. And if you notice here, the only thing that you need to know is you need to know Q value, you need to know H. H is the head at two different locations and corresponding R value. Okay. So if you know those values, you should be able to calculate K. And so as you see over here, there are two R value given and corresponding H value is given. You know also the flow rate. That means the only thing that's missing is K. So you can calculate K value. So I'm just going to write here K equal to, if you see the equations, Q times Lm R1 by R2 divided by pi H1 square minus H2 square. So if you plug this value, you should be able to get the answers for K in roughly should be meter per day. Okay, whatever that value, meter per day. And it says estimate the drawdown at the well. Drawdown at the well means at these locations. So you are given R0, but you are not given H0 or the head not given. So you can solve for that one. You can again put the same value. Now that you know the K value, if you put the same equation, the only thing that's missing here is the H value. If you know the H value, you should be able to get that answers. So again, let me add a new page so that you can, let's see, how do I add a page? Let's say one page, blank. So I ask you, what's the value? The B, estimate the drawdown. So that means at R0, what is the G0? Okay. So R0 is 0.15 meters. So you know G0 would be the original height, so that's 30 meter minus H0, whatever the head at that locations, whatever the head at this is H0. Okay. And so that means all you have to calculate is H0. Again, if you plug that equation, Q equal to, if you write this equation, Q equal to pi K. I'm just trying to look for that value. H1 minus, that's another H0. Because you just have to have conjugate number R1 by R2. So you just replace one with another, just have a known value and then everything else. So you know the K value. So this from, you know the value K from A, you know H1, you already know H1, H1 is given. Then you should be able to calculate the other values. Hold on, my pencil doesn't work now for some reason. Let's see. It works. All right, so H1 is pick anyone, any other than H1. So here H1 is 29 meters, R1 is 30 meters, R0 is 0.15 meters. You know K from A. Q is given 6,000 meter cube per day. Solve H0. If you solve for H0, you should be able to calculate G and calculate G0. Okay. So there is a question exactly similar to this question in homework. So you should be able to use this. Again, this type of questions, you just have to know what is not given and then rearrange the equation to find the answer. So the key here is the concept that you want to learn here is that if your flow rate increases, as the flow rate increases, the drawdown or the head will drop much faster. Okay, and your radius of influence or where you can collect water or capture zone would increase. And it's the same thing for a confined aquifer. You have equations, and then this is just another equation that shows how to calculate the capture zone. Because all you found out the head, but it doesn't say anything about this zone. Means this is the width of this area. So let me see. For some reason, my pencil stopped working in between some point. Okay, so this is the capture zone. So all you have to calculate is this width, and this capture zone is given. That's based on the flow rate and width of aquifer, and the V is the velocity. So it's written here, regional flow velocity. How far groundwater moves through the basically this is Darcy's velocity. That's not the actual water velocity. So if you know these equations, you should be able to calculate. This is just for one pumping well. If you have two pumping well, there is a different equation for that. So this is again capture with calculations. You should be able to calculate if you know the equations. So this is the common formula. If you have two equations, or if you have two well, that means your capture zone width would be 2 times Q over BV. If it is 3 well, 2 well. If it is 3 well, the width, this is W, should be 3 times QY BV. So this is the equations for number of well. So this N is number of well. If you plug this value, you should be able to get the answers. And these are the different this pi and fit. Fit is different angle. So if you know which location you are in, so you should be able to calculate that value. This is not needed for this class. All you have to do is the maximum width. Okay. So again, all these that we learn here is basically to calculate how much amount of flow you can capture based on the groundwater aquifer properties. If you know this much of water you're going to capture, you have to design your system for treatment of that much water. So I'm not going to solve these questions. It's exactly just plugging the value and getting the answer. Again, same type of question, draw down, radius of influence. Radius of influence is basically when drawdown equal to 0. That means if you have a pumping well here, you are saying that at what location, as the distance increases, r increases, whatever the r max, you don't have any more head dropping downs. So that drawdown equal to 0. That means your h head equal to h initial or before pumping. So that's the value. Try to solve this question again. These are the same type of question. We solved this one in CEE163. So I suggest that if you don't know how to do this one, go back and look at that lecture. So you should be able to find. But this is again plugging the value and getting the answers. For the same questions, these are all questions we have. Okay. So again, what you learned so far is if you know the aquifer, which is either confined or unconfined, you should be able to capture those groundwater. And so now, what is the advantage or disadvantage of this method? Ex-situ method, you are in control in the sense that you know exactly what pollutants you have in the ground. So you are collecting those groundwaters and you know whether this is being treated or not, because you can take the samples after the treatments and verify that there is no pollutant before you inject it back. The disadvantage, as I said, is expensive, particularly if your soil is not very conducive to groundwater flow. That means if you start pumping, it doesn't extract that much water. Um, and it can be incomplete treatment because of that impermeable zone. Some location will trap the pollutants. It could be expensive, particularly if it is go on for multiple years. So these are the different Ex-situ technology we have. Again, the first one is dig and dump. That basically you remove the source. Airstripping, we discuss about all that. Airstripping means um, you you inject a groundwater and then you actually, instead of pumping water out, you're pumping air inside. What it does, it basically you are creating bubbles through the soils. The and why it is effective? It is effective if you are removing volatile organic pollutants, because they are trapped inside the pore. So that means if they find air, they get into the air, they come out of that water. So this is only works for volatile pollutants. And another Ex-situ method is adsorption, which you learn already. If you have an activated carbon tank, you should be able to pump that polluted water through the activated carbon tank. So this works usually for organic pollutants or less water soluble. Because if it is water soluble, it doesn't adsorb that effectively. Then the third one is membrane treatment, which is basically removing any ions other than water. So if you use RO, reverse osmosis, most of the ions and most of the pollutants can be removed as long as they are big enough molecules. So this is effective for all pollutants, okay, because there are reverse osmosis membrane that is very selective. That means it can only let water move through it. So RO is most effective in most cases. But the problem with RO is our membrane treatments is very expensive. If it is the membrane can get clogged. Typically, your groundwater has very high salt content because of dissolution of aquifer materials. So those high salt contents can actually precipitate or create um, these clog the systems, because it will build up these high salt layers near the membrane. The next one is advanced oxidation. Advanced oxidation, we'll cover it today in the second half. That's basically if it is water soluble, and it can be degraded using highly oxidants or reductants, then you can do it. Mostly this is oxidation, that means you can oxidize. So this is usually, if it is water soluble, then you can treat them, because then you are that means you can disperse that oxidant very easily in waters and you can treat it. Um, Ion exchange works with ions. So this is mostly ionic, as it sounds, ionic chemicals. That means, let's say, nitrate. Nitrate is one such examples. If you want to remove nitrate, all it does, it remove the nitrate, but it replace nitrate with another ions, which is less pollutant. So for instance, you can replace nitrate with chloride. Then chloride is not a pollutant, nitrate is. So that means you can have a selective resin or ion exchange resin that could remove a nitrate and replace it with a chloride. Bioremediation is, we are going to cover it. That can be applied only biodegradable, as it suggests, biodegradable. And not all pollutants are biodegradable in the time scale that we are interested in, because you are pumping so much water, you have to release it back at certain rate. So that means you are limited by how effective the biodegradation will be for to meet that pumping rate. So a lot of times Ex-situ method is not, they don't use biodegradations if you are pumping lots of water. The last one is thermal incinerations. That's not necessarily effective always. That's basically source. You burn the entire or the incinerate the soil at the source zone. All right, so that's all for the Ex-situ methods. I'm just going to cover a little bit of carbon, but we are not going to cover this one. I'm just going to explain what these different terms means. But next 15 or 20 minutes after the break, we'll discuss the chemical oxidations. Then we'll discuss the project. So we have a 10-minute break. We'll meet at 5:15. If you have any question in between, you can put on chat. Let me see, there are questions. Um, what is the aquifer width if it is not confined? There is no aquifer width if it is confined. You are just looking for the head or the height of the water. Oh, Emma has already answered that. Great. Okay, so let's meet at 5:15. So before the break, we discussed about different Ex-situ treatment technology. Now we are going to, I'm just going to explain the brief overview of different, the key treatment technology that we are going to cover in this class. The very first one is carbon adsorption. Carbon adsorption means this look like this. What it means that you pack activated carbons, either powder form or granular form, mostly granular form, inside this blue tank, and then you put them in storage. And so part of this class, you are going to design this treatment system. Means you are going to tell how much activated carbon you need, how big the tank size should be, what should be the flow rate, how you pack them, all that design configuration you learn it. And that only works. This carbon adsorption is pretty popular technology, and the one that you use is activated carbon. Um, and usually this is most popular because it's cheap compared to many other treatment technology. And normally the side effect of this technology is you have to dump with that, you have to deal with that spent activated carbon. That means you have to dump it in another landfill. So that's the risk. And also activated carbon, um, once it's exhausted, it's very difficult to reuse unless you regenerated the capacity. So learn all that. But most importantly, what pollutants you can use to remove activated carbon. As I explained before, this is only works if you have organic pollutants. Some metals can also be removed, but then you have to change the surface property different way. but mostly I would suggest that this is organic pollutants um, with low water solubility. Those are most effective to remove. Okay. Then you have air stripping. Air stripping tower look like this. So the principle of the overview of this technology is this works only if you are if the pollutants are volatile, because that's how it sounds like. You strip that pollutants from water, contaminated groundwater, into air, and then you capture that air and you treat them. So this works for volatile pollutants. Unless it's volatile pollutants, it's not going to work. And the idea here is that you spray water. So you spray contaminated water. Okay, so you have a tank here. You put contaminated water. So this is polluted water. So you have a nozzle here. You spray it, and then you also um, blow air through it. So blow so air in. So this clean air in. So the idea here is you spray like a shower and you blow air from the bottom. And then the idea here is that these water droplets will interact with the air, and then the volatile organic pollutants will find that air-water interface and strip out of the water. So the idea here is that you as smaller as possible or the larger air to water interface. Uh, Normally that doesn't work that way. You don't really spray anything on it because the area of the spray depends on the bubble, and bubbles are very expensive to build or to make because you require high pressure. So that's why a lot of times what people do is they add some kind of high surface area plastic material. So that means if you just by allowing the water to trickle through that and letting the air drop from the bottom, that solid shape or the structure itself provide the high surface area, and the fact that air is around, so that would strip out of it. So that means there are some packing materials here. Packing materials with high surface area. The idea of high surface area that provide that interface to air to water. As the water flow through it, the air, the pollutant will strip out of it. And so the type of design you are going to look for is what's the flow rate of air, what is the flow rate of water, what is the packing, how you are going to how high it should be, and how to calculate the transfer rate. All that factors is going to be your design factors in this class. Not this class, in the following class you are going to learn all that techniques. And so now what you learn here is that you have if it is volatile pollutants, they are stripping. Non-ionic or low solubility is going to be adsorption. If it is ionic or highly water soluble, use oxidation reductions. Again, all these Ex-situ technology has always high capital cost or operational cost, because you have to continue to operate. Somebody has to be there, and it also produces secondary waste because it doesn't really degrade the pollutant. All it does, it transfers the pollutants from one phase to another. For instance, here, all it does, it remove the pollutant from water to air. It doesn't really destroy it. Here, you remove pollutant from water to activated carbon. So again, you are not creating, you are also creating another types of polluted materials. Um, Oxidation, it destroyed. Okay. So that's all in terms of the technology. And now coming to the oxidation reductions, the only thing you have to remember here is there are multiple type of oxidants you can use. The idea here is that you create the oxidants, either you buy it, store it, and disperse it in water, or you produce the oxidant right there. So the degradation rate is always first order kinetics, means if you have a pollutant concentrations, it's always change at the rate of Kc. So this is the rate constant. So this is called first order because change in concentration depends on concentration to the power 1. Okay. And so the if you solve this equation, this will be exponential function. So this will be C equal to at any time uh, C0, that's the initial concentration to begin with. That's the groundwater pollutants concentrations time e to the power minus kT. So this is first order. Mostly you can assume. So to design this kind of system, you got to think of this value, the K value, because that's the only thing you can control. Because time is usually limited to the flow rate, how fast you are moving, and those are time available, so you can't really change much. So the only thing you can control is the K value, and that K depends on different type of reactant or the oxidant. So here you have 4 type of oxidants commonly used. So what you have to learn from this particular slides is which oxidants to use when, and what's the advantage and disadvantage. The first one is ozone. Ozone is basically O3. O3 is extremely reactive. So your K is high if it is reactive is very high. So ideally you want to have K as high as possible. If K is high, that means it takes less time for you to degrade a pollutant. But there is a disadvantage of K to be high, is that if it's so reactive, sometimes it reacts with itself, and then it's not stable. That means if you store that pollutant or oxidant at the site, it will become destroyed by itself. Okay, so that's the case for ozone. Ozone is very reactive. That means the moment you produce the ozone, if you don't use it immediately within few minutes, that ozone is going to become O2, oxygen, which is not that reactive, at least in this state. So that means this when you are looking for ozone, you have to produce the ozone at in situ. Means you have to produce that ozone at the site you are going to use it. You cannot transport it from somewhere else. So no storage. For ozone, no storage. Because extremely reactive, it will destroy to become oxygen. It will degrade to oxygen. So ozone in situ productions. So now the other aspect is ozone is UV light. UV lights is the last one I wrote. Um, Thus you can produce any location. It's basically UV ray. So as long as you have a diode, you can produce UV lights. You can even buy UV lamp in Amazons. So UV lights is not difficult to produce. The lamps are very easy, well made, and it can also be switched on and off. That means you don't have to recreate. For instance, ozone you have to create and then you have to use it. UV light you switch off, then it's gone. So it's very convenient production. So there is less waste. So UV lights are very popular. The Then why people are not using it? Well, the reason is UV lights are sensitive to the depth of water. So that means, like any light, it doesn't penetrate below certain depth of water, because there will be particulate, there will be stuff, they will react with UV light at the surface. So think of a tank of water. If you shine light at the surface, most of the reaction will take place where the light is. As you go below, much farther from the light, the intensity decreases or the by power functions. So that means if your distance, even if like within like 3 centimeter away from the lamp, your UV lights is intensity is a lot lower, and it's also decay much faster by reacting with water and everything else or other constituents. So that means it's not very effective unless you have a real good contact time. And if you have too much other color materials like organic carbons, particulates, UV lights it will be blocked. The UV light will be blocked. Okay, so that's another ineffectiveness related to depth. So now leave behind there are two other things: hydrogen peroxide and chloride. Between those two, hydrogen peroxide is reactive. Chlorine, some the chlorine gas, the OCl is not that reactive. Okay, so why it is important? This is important for wastewater treatment plants. And hydrogen peroxide is very easy to is highly water soluble. This is water soluble. If it is water soluble, it's very easy to mix. That means you don't have to worry about like UV lights where whether you can mix or all the pollutants can be reacted easily or not. So that means you will use hydrogen peroxide when you have easy to mix, easy to mix. So that means if you have a water soluble pollutants, you are most likely effectively degraded by hydrogen peroxide because you can reach out to everything together. Chlorine gas, again, it's not easy to mix. It's a gas, so always have a difficulty. But if you convert that to OCl, which is the bleach, then it will be effective. So again, these are the different advantage, disadvantage you have to think of, and those will determine what to use. But everything else is much more um, simplified versions. So now to know how do you know which one to use, basically this reaction tell you some example. It's hard to see because I lower the quality, but you have the handout where you can check. What it means that it gives you a NaCN is a cyanide is a type of pollutants you might find in some water, and you can oxidize using different types of reagents, oxidants. So these are all the reagent given, and it gives you equation that tell you what's the byproduct. Okay, so if you know this equation, you can tell how much moles of oxidants is needed. Again, you may not see that here, but you can look at your handouts. There you can see it clearly. Okay, this equation is just to determine how much moles of oxidant is needed. And one of the things is that oxidant is a redox reactions. So that means that that treatment depends on how many electrons it can receive or it can you can give. So that oxidation reduction reaction or the activation energy depends on the free energy here, and that's given over here. Okay. So when you think of oxidant, it's the energy is positive or the volt needed is positive. It's a reduction, it's a negative term. So higher the positive terms, the more high effective oxidant it is. And so that's based on free energy. The reason I put it here is that to show that any reaction depends on also temperatures. Free energy is related to temperature, so that means if you warm up that entire reactants, your reaction will be more efficient. Okay. All right. So there is nothing more in terms of what to learn here. The only thing that relevant for the homework is to calculate how much oxidant you need. I'll give you just this one example. That way you can solve the similar questions in the homework question number 1. So this example is calculate the amount of chlorine gas required to treat 20,000 gallons of waste containing 270 milligram per liter of cyanide. Okay. So you are pumping this much water, 20,000 gallons. So the flow rate is given, or the volume is given, 20,000 gallon, which you can convert to liters. So which will be 20,000 1 gallon is 3.785 liter. So this will tell you the number, whatever that value in liter. And it says that you have to treat that entire volume or remove all the pollutants, and that concentration of the pollutants there is 270 milligram per liter, concentration of cyanide. Okay. If you know this one, then you know the amount of cyanide in that particular um, the water. So the mass of cyanide that you need to remove is concentrations times volume. Then you know this much amount you need to treat. If you know the mass, you know here that 5 moles of chlorine is needed to treat 2 moles of sodium cyanide. Or another way to say is, from this reaction, you know 5 moles of chlorine required to treat 2 moles of cyanide, because 1 mole of NaCN is sodium plus cyanide. That means 1 mole of sodium cyanide is same as 1 mole of cyanide. That's why I wrote 5 moles of chlorine is required to treat 2 moles of cyanide. So 5 moles of chlorine means how many grams? If you know chloride atomic weight 35.5, so that means 5 times 35.5 is chlorine, 35.5 is 1 chlorine, and you have 2 chlorine. So this should be, let me see, 5 moles per chlorine, and 1 mole is 35.5 times 2. That's the atomic weight or molecular weight. So that will be 71. So 71 times 5, that will be gram of chlorine. So that means what I'm saying here is if you take 355 gram of chlorine, you will treat 2 moles of cyanide. So how much 2 moles of cyanide means in terms of gram? That will be 2 times carbon is 12, hydrogen is 14. So that will be 6, 20, 26. 26 times 2. So that will be 52. So all I'm saying here is based on these equations, 352 gram of cyanide is treated by 355 gram of chlorine. All you have to do is how much gram of cyanide present in your groundwater, and that's written here. Okay, so that's 270 milligram of cyanide per liter, and you know that 1000 gram of cyanide is 1000 milligram of cyanide is 1 gram. So I'm just converting to gram. Then you know that 52 gram of cyanide is equivalent to 355 gram of chloride. Okay, so cyanide cancels, and then you have to, because this is 1 liter, this is the amount of chloride needed for 1 liter of groundwater. But you have how much groundwater? 2000 gallon or 20,000 gallon times 3.785 this liter. So this will give you the amount of chloride in gram. Okay. So this is exactly the question number 1. Okay, give you a multiple question there. Just have to use the equation to solve it. So the idea here is that you know how much amount of pollutants you have in certain amount, certain volume of groundwater, and then using the stoichiometry, you will be able to convert that to how much amount of oxidants you need. So that's all in terms of the homework question related solution here. So a couple of things for design considerations. This is relevant to quiz or your own projects. So when you design this oxidation treatment system, first you have to think of what are the different other chemicals present, because the moment you add these oxidants, they will also react with those non-targeted chemicals. For instance, many groundwater may have some organics, dissolved organic carbon. They can also be reacted with these pollutants. So you this kind of oxidants. So that means if you have any of these residue and reactive residues, you have to add more oxidants. That will reduce the cost, or that will increase the cost. So for that kind of system, you have to first remove those extra pollutants. And second thing is the moment you add oxidants, they can also form byproducts. For instance, just because you have a contaminant, you degrade it, they will form another chemicals that could be also more harmful. In fact, if you have lots of organic, they can form carcinogenic pollutants. And as I said, you have to choose different types of oxidants. You have to think whether you can store them or you can use it. For instance, storage. Ozone you should not use, because once you store it, this will no longer be ozone. So if your storage is a concern, you cannot use ozone. Okay. Um, you can store hydrogen peroxide. So then that means that's the right kind of oxidants. If it is mixing is required, your gas are not easy to mix with water. So that means hydrogen peroxide is easy to mix. Um, is easy to mix. Okay. Then another thing is if you have a colored, let's say you're like think of a tea bag, that has so much color that will block the light. So that means if your if your wall sample has high color because of organic, you should not use UV light because that will be blocked. Okay, so the color that means your UV light is not going to be effective because of blocking the light. All right, so now that we learn everything, so let's see this quiz, last quiz, so that we see how much we learn. Which oxidant can be easily mixed with water? You have 20 more seconds to answer it. Just know the hints that anything gas you cannot mix, light you cannot mix, because you can only, so UV is light, that means you can't mix it. All right, so I'm going to close the poll in 5 seconds. All right, so are the results. So there is a mixed distribution. 17% says C, 17%, 8% here, 75% this one. Okay. All right, so UV light you cannot mix. Okay, that's easy to explain. Ozone, it's a gas. Okay, so it's the moment you bubble it, you have to bubble heavily, and then the gas can always go up. So that means once it goes to the head, you cannot put it back again. Okay, so that's why it's not very easy to mix. Same thing for chlorine gas. What's easy to mix is if it's a liquid. Okay, so and hydrogen peroxide is a liquid, so that's why it is going to be easy to explain. All right, so that's all in terms of the class today. What we are going to do in next class is learning about carbon adsorption, activated carbon tank, and air stripping design. But before that, I want to just again highlight that the project topic. Send me a Google Doc and write your titles, write the team member's name, write your thought based on what I just suggested. um, Make it specific, and whatever you submit you get full points, because this is not by mean to be accurate or final. I'll give you comment immediately within 5 minutes, or it takes 5 minutes for me to give comments, so that basically I'll give you some question to think about, because the next thing is once you decide your topic you will define your outline. So these are the these discussion will help you to come up with outline. You'll go back and start reading more materials and come up with outline. So every step of the process, you can just tell me that Google Doc we have updated. Can you look at it? So I can just immediately check that and give you comment. So you don't have to really meet for this. But if you want to meet, send me email. I know that I'm meeting one group. It's not required. All team member doesn't have to be present for this meeting. Just let me know whatever times it works. Okay, and from the following weeks, once you have the outline stage, we'll have office hour where I will be available for that hour. Any of the group members can join in that time, and we go through the outline to discuss. Again, I'm helping you to write the project, so this is consider me as part of the team. So we'll discuss and brainstorm together, and not just me, also the TA. Attend the TA discussion hour. You can ask the TA about it. All right, so that's all for the class today. Any question? I'm going to stop the share the slides. Okay, well, we have still 8 more minutes, but we don't have to stay here if you don't have any questions. I'm here. If you don't have question, you can leave. I'll just wait a few minutes in case anybody has questions related to project. I'm going to stop the recording.